Sampling principles, making inferences with confidence. We sample so that we can make inferences about a population of interest. Inference is the process of generalizing characteristics of the population from the sample, and usually we make our inference with some measure of precision and confidence. To make inferences about a population, we sample from that population, usually repeatedly, and we report estimates of central tendency and variability. The mean is the most common expression of central tendency, and the standard deviation is the most common expression of variability for samples. We can report estimates from a sample as either a point estimate or an interval estimate. With point estimation, we estimate a single value. So we would report x, for example, from a sample as an estimate of the true population mean, mu. With interval estimates, we report an interval, so the estimate includes a range of values, most commonly reported as the mean plus or minus the standard deviation or plus or minus the standard error. So let's take an example by looking at this sample of leaves in the image below and look at the width of this leaf. If we were to report a point estimate, we would simply report the mean equals 1.5 centimeters. Note that we always include the units of our estimate, of our measurement, in our estimate. Now this tells us what the mean value from the sample is, but it doesn't give us any information about how much variability, which we can see there's quite a bit of variability in the width of these leaves. If we do an interval estimate, we would report that the mean plus or minus the standard deviation is 1.5 plus or minus 0.5 centimeters. And so we're providing information not only about the central tendency, or the point, what's in the middle, but also the range of variability of our sample. When we're reporting the precision of estimates, they can vary for several reasons. First and foremost, the inherent variability of the population. Now remember, when we're sampling, we want to be able to capture that variability and in our sampling in order to report that. But different variables assume, some variables assume values that are highly variable and others are relatively stable. So for example, if we consider the number of petals in a wild rose flower, in general, wild roses have 5 petals. There's occasionally variation in nature, but in general it's relatively invariant. Another example of a variable that has more variation in the population is the number of hairs on the head of adult men. Sampling error is another source of variation in the precision, so that just due to chance selection of sampling units from the population, we can get variation in our precision simply because we're selecting a subsample of all the sampling units that are available. Sampling design is another factor that can influence the precision of our estimate. So the decisions that we make about sampling units, the type of sampling units, the sample size or the number of sampling units, how we place them in the landscape, etc., can have quite a bit of effect on the precision of our estimate. To make inferences about the population from the sample, we want to include a statement both about the precision of the estimate and also how confident we are in that estimate. We do this using confidence intervals. Confidence intervals include information about both precision and confidence. A confidence interval is usually stated as an interval around the mean, and we see this stated in two ways. First, we will sometimes see it stated as the mean plus or minus a value that represents the term S sub x, or the standard error, times t. Here's an example. A 90% confidence interval equals 140 plus or minus 15 grams per meter squared. Note that in confidence intervals we also always include the unit of measurement. Another way of reporting a confidence interval is as just the interval. So we report the lower limit and the upper limit of the interval with the mean in the middle. For example, this same example, a 90% confidence interval, would be 125 grams per meter squared less than or equal to the mean, which is less than or equal to 155 grams per meter squared. Essentially, we're saying that the mean, the true mean of the population is 90% confident, we are 90% confident that it exists in this interval. Confidence intervals have both a confidence level and a width. The confidence level expresses the amount of confidence that we have that the true mean, mu, is included within the limits of the interval. The confidence level is set by the investigator, and it affects the t-value part of that term. The standard error, S sub x, reflects the precision of the estimate, and the width changes with both the precision and the confidence level. So let's look at this a little more closely. The interval width is represented by the term S sub x times t, and t is a value that reflects both the error rate, alpha, and the degrees of freedom, which is the sample size minus 1. The confidence interval will be narrower if we have greater precision, because with greater precision the standard error is smaller. It decreases in value, so the term S sub x times t is going to be smaller. The confidence interval is also narrower with smaller confidence levels, because t-values decrease as we decrease our confidence level. So that term S sub x times t is going to be smaller. Let's look at an example. In this case, we have a sample size of 20, so the degrees of freedom is 19, and for a 95% confidence interval, that's an error rate of 0.05, the t-value is 2.093. For an 80% confidence interval with an alpha value of 0.2, the t-value is 1.28. And simply by changing the value of the t term in this larger term, the interval is going to be smaller. Let's look at an example. In this case, we're looking at a population of plants represented in this diagram. There are 20 quadrats that we have used to estimate the density of plants. If we develop the 95% confidence interval, that is 4.0 plus or minus 2.3 plants per quadrat, we're stating that we are 95% confident that the true mean mu falls within the bounds between 1.7 and 6.3. We are also saying there's a 5% chance that if our sample mean does not fall within this bound, we're willing to make the wrong inference. With an 80% confidence interval, the that interval is 4.0 plus or minus 1.5 plants per quadrat. So we're saying that we are 80% confident that the true mean mu falls between 2.5 and 5.5 plants per quadrat. We're saying that we're 80% confident that the true mean falls in this range, and we're willing to accept a 20% chance that it does not. We're willing to draw the wrong inference 20% of the time. Now let's look at an extreme example, which is a 50% confidence interval. In this case, we're saying that we're 50% confident that the true mean falls between 3.2 and 4.8. By saying that we're 50% confident that the true mean falls in this range, there's a 50% chance that it does not fall in this range, and that we're willing to draw an inference, the wrong inference, 50% of the time. It's very unusual to see a confidence interval reported with this low level of confidence. Let's look at another example where we hold the confidence level the same, but we have difference in the standard error. So this is an application where we want to evaluate the success of mesquite control, comparing mesquite cover in treated and untreated areas. If the means are different with 90% confidence, we would infer then that the control treatment reduced mesquite cover. So here are the results of these sampling efforts in a treated and an untreated area. The mean value in the treated area is 20% versus 40% in the untreated area. Based on differences in the precision of these estimates and holding the t-value the same, because we're developing 90% confidence intervals, we would say that we have a 90% confidence that the true mean in the treated area lies between 13.4 and 25.5% cover, and that the true mean in the untreated area lies between 28.8 and 51.2% cover. Based on these results, we would then infer with 90% confidence that the mean cover of the mesquite in the two areas is different. We make inferences with confidence. Inference is the process of generalizing characteristics of the population from the sample. These inferences are usually made with statements about precision and confidence. The precision of our estimate is affected by the inherent variability of the population, sampling error, and sampling design. Confidence intervals are used to provide information about the precision of the estimate and how confident we are that the true population mean is included within the interval.